So now that we have an idea of what return-oriented programming is and how to actually be able to execute different kinds of code if I can control where I return to, I'm going to show a couple of different variants, well, one more variant of Spectre before we carry on, making use of what we call a gadget. A gadget is just a little chunk of code in the victim's space that I as the attacker, can cause to execute. And so return-oriented programming is one of the ways we can do that. The second variant of Spectre that I'll show you does that as well. But before we do that, I want to just give a complete overview of Spectre version 1, and then we'll talk about Spectre version 2. So the basic step-by-step is safe victim code, right? Victim code that is not suspicious in any way and might even live in an existing library or something, or be injected via a plugin, introduces a bound check, right? It's a boundary check on an array, and that dummy array doesn't even matter what's in it. All I have to do is control that variable to the array. Then I flush the cache, first of all. Then I mistrain the branch predictor to expect that x is always going to be less than the array size, or most of the time. Then I set x to the offset from the dummy array to the secret I want to steal. That failed boundary check starts to execute because we haven't resolved the failed boundary check yet. Right? This is the key point of this speculative execution attack is until we resolve that failed boundary attack, we're going to start to execute the next instructions. Once this boundary check resolves, the machine is going to say, oh, I made a mistake, and it's going to walk all this back and start to do the next thing. But in the meantime, we will have already been able to steal the secret. The secret data that is at the array plus x is going to be used as an index into a large spanning array, or we call it the probe array, that is going to, depending on the value of the secret, cause a different cache line to load. And then I'm going to probe the cache to determine which line was loaded using a timing attack. And knowing the index of the cache line was encoded, that is the value of the secret that I want to steal. And in pictures, it looks like this. So again, the attacker, all I have to do is control X. I trick the victim into accessing the secret, and in the time it takes for the victim code to realize that it's made the wrong branch prediction and walk all that back up, I use the secret to access as an index to access a probe array, which causes a cache line to load, which allows me to read the secret as the index of the cache line. Super cool. The second variant makes use of a different kind of speculative execution. Instead of training up a branch predictor to say go, no, go on a branch, we're going to train up a branch target, which means if instead of deciding whether or not to branch, I have to decide where I'm going to branch to. In modern instructions, we usually call these indirect branches. We call them jumps because we're putting a new address into the program counter so that the machine can jump to a new address, right? We're going to jump to a subroutine and come back, a very common process. Until that instruction resolves, I don't necessarily know what the target of the branch is going to be. But if I can guess, I can start to execute code at the target of that branch, or target of that jump, just speculatively, right? Just in case it happens to be true. And again, if I got the prediction wrong, well, I just throw that stuff away and start again. And so like a branch predictor, we have a branch target buffer, which is going to keep copies of the previous addresses that we have branched to, or other ways to predict what the address of the branch is going to be. Again, these should be jumps, not branches, but that's okay. Keep copies of what we predict the address of that jump is going to be. And then if I can manipulate that branch target buffer, which again is a shared resource, then I can trick the machine into executing different kinds of code. So similar in a lot of ways to version 1 is I'm going to still use the same kind of cache attack. Well, maybe not. But similar to version 1, I'm going to trick the victim's code into training up a branch predictor in a certain way, branch target buffer in this case, and then I can use that to execute code. So specifically what I do is the attacker, I can jump to an address in my memory over and over and over again, training the branch target buffer. And because the branch target buffer is shared, it will then predict that same address for the victim's memory. So all I need to know is where in the victim memory this gadget that I want to cause to execute is, and then I can jump to the equivalent address in my memory, and that will train the branch target buffer to jump there when you get a misprediction. Now, it's not going to be able to execute all of it, or maybe it will, right? All that execution will be speculative, waiting for the jump target to resolve. And once the jump target resolves, oh, this was wrong, throw it away. But in the meantime, things have happened, code has executed, and I can make use of secondary effects of that code, right? I can look at the cache timing or whatever, all these little microarchitectural changes that might happen as the result of the code that don't get walked back when we discover that we made the wrong prediction and flush the results. So that's the main trick, is that you have to be able to identify microarchitectural changes in shared resources that don't get walked back when we mispredict a branch. So very specific situation, but in fact causes several different kinds of executions, several different kinds of exploits to happen. Spectre version 1 and version 2 are just a couple of examples. And in subsequent videos, I'll show you a whole collection of different kinds of speculative attacks and how they work.